This is the third day of our course. And today it will be divided into two parts as well. The first one will be related to numerical methods with Julia. And I will be presenting this part. And of course, the rules are exactly the same as before. If you've got any questions, just ask, put it on the chat, and we will try to answer. Of course, if I know the answer. And we've got both code and presentation. So I will be switching between those. And the code is available for the whole course. So I will get it, like the packages. If you need to install some packages only for today, it's still time to do that. And let me start with some high level title. Why do we need numerical analysis? So not only with Julia, but do we need it, or actually is it usable? And from the perspective for the ordinary user or the people on the streets, should they be aware of numerical analysis? And the presentation outline will be, I will start with some examples, like everyday life examples, I will say, and getting some application areas. Then we'll get through basic examples in Julia as well. But after that, I will get into details with Julia. Anyway, I will be switching because it's not like all the examples are in one place only or the other. Sometimes it will be explained on the slide, and the implementation will be, of course, in Julia. I will end up with a brief conclusion that is related with both Julia and numerical methods. So let's start with application areas. Of course, there is no theorem that, oh, those are the six areas when the numerical analysis are the most useful. But maybe the idea behind numerical methods is the something that you should understand. Everyone should understand the best. So usually people think that without computers there is no numerical methods. Actually, it's not true. But the concept, of course, is right. So there is one good example of the need of numerical analysis and numerical methods in general. And this example is about thinking simple real numbers. So we know that there are infinitely many real numbers, but everything related with computers is finite. So there is no possibility. If you've got the supercomputer, still there is no possibility to put something that is infinite number of something that is a lot, still a lot, but too much for any computer, any memory, any hard drive, any server, anything, like even if it's a cloud computer. So you can scale it, but you will, at some point, you will have to deal with the thing that you will get only approximate solution. The question is not if it's an approximation, but the question is how accurate the solution is. And in most cases, you don't need exact solution. You don't need even accurate enough. So accurate enough for your needs. Like in economy, if you deal with money, then usually it's 2 or 4 digits after decimal point, and you don't need much more. But in physics, it's not the case. You will need some more, because if you got the particles and the energy of those particles, that you will need much more accuracy than this. So it depends. It depends on the area of application. But in all areas, you can point some kind of I will call it maybe not application, but there are algorithms that are well known, sometimes for a century or more, but there is not a revolution, but evolution of those algorithms because, for example, we are able to get the distributed computing, and because we've got more memory, so we can do better. or simple. There are some different needs, like from AI. Some different needs, different application possibility of application, and this evolution is regarding the it's not only mathematics or astronomy. Right now, it's usually machine learning or artificial intelligence, but it could be in military, it could be in healthcare, it could be in many other applications. So, because most of the students listening to the course are from mathematics, then I will not go into details with those specific areas, but I will say that from the business point of view, those 6 are the most usable in. So if you cover all those 6, then probably you will cover like 99% of cases that you will need to make analysis. It's the numerical analysis used for. And the first one, of course, is the interpolation. And there are plenty of examples of interpolation, even computer. If you think of the computer graphics, it's a kind of interpolation. So computer plots like 3-year-old child. So putting the dots and connecting them. So this is a kind of interpolation. And you've got also other more sophisticated cases, for example, with the face reconstruction or the building reconstruction in architecture. You will need the interpolation there because you know there is a hole and you want to fill the hole in the way that it was before. Extrapolation, it's something that you use if you want to go outside. So, for example, for a casting, it's a kind of extrapolation, time series extrapolation. So you already know some kind of values, and you want to use the same function, or the class of function that was fitted to the observation you've got. Regression, it was already covered yesterday. Of course, by regression, I mean all the types of regression, not only linear. You've got logistic regression, you've got lasso regression, you've got plenty of other cases. But the idea behind it is more or less the same. You've got the statistical process behind it. And even if you think about econometric modeling, it's still mathematics behind. Yeah? And the relationship you want to discover, machine learning, it's still not a black box. It's math, more sophisticated, and maybe you can't do this on your own on a paper because it's too difficult, but still it's a math. And those the relationships that you want to discover, the pattern and or identification of some undercover things that are in the data or to explain some kind of phenomenon, it's still one of the use cases that is used in plenty of other areas. So not only in economy, but if you think about data science in medicine, in military, in investment, banking, finance, chemistry, physics, all of them, it's more or less the same. Approximation, it's not the same as interpolation, because if you choose the measure, you can do much better. And finding those unknown functions that will suit it for, of course, to the data, then you can do better, because you can, for example, change something that is much too complicated for us to something that is easier to deal with. And this kind of approximation, of course, with the acceptable accuracy, that is something that is done. And even with AI, like you've got the ChatGPT, it's not accurate, but in some cases it's accurate enough. Yeah. So system of linear equations, I pointed this outside of the regression, but those kind of system of linear equations are still inside the regression, inside the interpolation, inside the approximation. It's like a brick you are using in other areas. And this brick, it's still evolving. Why? So it's more sophisticated, because if you can get more, you want more. So why to stick with 1 million variables if you can get 1 billion? Yeah. So you can get better accuracy, and linear is something that should be easy. Yeah? It's not always easy, but non-linear things are much more difficult. Even if you want to solve something that is not linear, you still need to know how to how to deal with linear things, because usually you've got plenty of different linear equations and solve them if you want to solve one problem that is non-linear. And the last one, it's like differential and integration equations that this is difficult, but it's not for ordinary people anymore. But if you think about applications of this one, airplanes, cars, building things, simulations, or predicting the weather, in all of them, there are some kind of problems that are related to ordinary partial or integral differential equations. And this is of course more complicated, but if it's more complicated, then the mathematics used on a computer is the best there. Right? So it shouldn't be better than people. It shouldn't be smarter than people. You should use computer and Julia in this case in a smart way to solve some problems, to find some new answers or new applications in a way that will be beneficial for people, for society, for you, for your company, for anyone. Yeah. So those 6 areas, of course, I can't cover it because each of those is at least one semester course in mathematics, computer studies, physics, or etc. But to give you the hint, what kind of problems you can solve using Julia. So those kind of problems you can do, and this is it's not complete area of problems, but I put it Julia packages, some exemplary Julia packages for solving some kind of problems. For example, if you want to solve linear equations, you can get linear solve. If you want to use sparse matrices, there is a specific Julia package for that. For almost everything you can think of in mathematics, there is a package already in Julia. Sometimes more than one, so you have to try which one is for you, or which one is, for example, faster, which one get more options, which one is more for you, for your application. But there are plenty of different packages that you can use. For example, if you want on only polynomials, on only integration, or only optimization. Some of those will be used today or tomorrow, for example, for optimization problems or for differential equations, but not all of them, because there are hundreds of the packages. So today, during this course, we will use only 4. And for the specific ones, not plotting only or data frames that were already covered yesterday, linear algebra and special matrices. So those 2 I will use just to show some examples of how you can use it. So right now, let's get into examples. So the first part will be maybe not exactly related to Julia, but I want to convince you that Julia is the right package, right software to use if you want to deal with this kind of problems. I said that it is not true that without computers there is no numerical methods, and this is a proof of what I'm saying. And without computers, there were still algorithms before, and as you can see on this picture, you've got the Babylonian clay tablet. So we've got 7,000 years BC, and this is so thousands of years, and you've got some kind of numbers there, and people were thinking what it was used for, and they come up to the conclusion that this is simply an approximation of the square root of 2. It's not hard to understand why they were using this, because at the beginning, the mathematics was used for the purpose of building houses, buildings, constructing things. Yeah, So if you've got the unit square, you know how to calculate some square root of, you need the square root of 2. With calculators, it's pretty easy for us to calculate it. But imagine that it is 1,000 years ago, without computer, without even paper, and they still were able to get quite good approximation of the square root of 2. And today's, so you can compare it. Today's calculations are below, and in here, if you see how many digits they were like correct. So 1, 2, 3, 4, 5, 6 on the 6th place after decimal point. Now, there is a discrepancy. So it is pretty good. And after that, there were plenty of iterative numerical algorithms that were used by people to simplify the work, to simplify their lives without computers. Of course, with the computers, it was speeding up a lot. And right now you are using numerical methods almost everywhere, even without knowing that. But this is an example that even without computers, there were numerical methods. And so let's get to the examples, because they will be probably beneficial. Maybe some of them are known for you, but the application in Julia, so how you can solve it in Julia and what is it good or not, it will be the target of this course, this part of the course. Let's at the beginning, for the first example, let's think how small is 0. This is a tricky question, because from mathematical point of view and exact arithmetics, it's an obvious answer. But think on a computer, and any, like if you get any computer, a supercomputer, plenty of memory, it's still at some point there must be a point from which 0 is indistinguishable from the small number. And the question is how small number for computer is the same as 0. And it should be pretty easy to check. And how to do that? So if you start from some number like 1, and you will be dividing it by 10 or by 2 or by any other number, and you will continue to do that, at some point you should get to 0 on a computer, of course. And the first task is to find the smallest number for which this is simply a 0, and let's get the power of 2 of the power of 10. I will switch to the Jupyter, and in here this is the task. And in fact, there are two examples, because in Julia you've got from the first day of the course, you know that there are types in Julia, and it is pretty good. And depending on your needs, you should choose the proper type, because it will speed up your computation. And we will start with the float 32 data type. And the loop is in here. So I will start from x, from 1, like so the x is 1, and I pretty much know where to end. So I will divide in each loop iteration. I will divide it by 10, and I will print the result. So if you run it, if you run it, you can see that it's smaller and smaller and smaller. But at some point, let's find this point. At some point, you will get 0. And of course, you can do this in any software. So you can decide, verify how good this software is. At this point, so if you use float 32, then, so in this kind of architecture, then this is the last thing that is not 0 for computer. After that, you will get only zeros. Okay, but you can do better. So in Julia, you can get types that are with better accuracy. So one of them with better accuracy is, of course, not float 32, but float 64. And the disadvantage of it is that you will need more memory for that. The code is more or less the same, but you can't use only 50 iterations, because it's better, the better accuracy. But the idea is exactly the same. So let's see what is the result. And by the result, I mean, let's find how good it is right now if you change this type. So it's much better than before. By much better, I assume that it is not expected, but and in here. So get twice more memory gives you this much improvement. Instead of 40 something, you will get 300. Yeah? And of course, you can exactly find out what is the arithmetic precision in Julia. And for that, you should use function at epsilon. So this is the smallest absolute value for the specific type. So if you use it for the float 43 and float 64, you will get, in fact, something like that. What does it mean? It means that it's not as good as you think. I mean, the standard computer and arithmetic computer arithmetics with double precision, it's 16 decimal point, only 16 digits after decimal point. Only, or so is it a problem for physicists? It's a problem, but in real time, it's in real life is pretty much enough. So it's not as good, but dividing by 10, this is pretty easy. So it's not that you can use any number you want. Double precision is a standard today, 16 digits after decimal point in any computer. So you have to use a special type or special arithmetics if you want to do if you want to do better than this. But this is one restriction. The second restriction is that, of course, if you've got this kind of type, you can't do even. We see how small it is, and right now you can reverse the question: how big numbers we can represent. And for that, you can use float mean or float max for those types, and you can see how big or small numbers, yeah, you can even represent. So arithmetic precision is not as good as this one, but you can represent numbers to this point. For example, for this one, it's 10 to the power of 308. Yeah, so you can present it. You can add small and small number like in this magnitude, but the precision of all the arithmetic operations will be till 16 places after the decimal point. Yeah, only. And of course, big numbers as well. Yeah, you can see how big numbers you can represent. So there are some restrictions, and there are restrictions for the computer arithmetics, not only Julia arithmetics, but computer arithmetics. So why Julia is good? Julia is good because it's for numerical methods. All the operations that you are performing using Julia are written in an optimal way. So what I mean in optimal way, to minimize an error. To minimize the error, not so you will get the result, and probably you can't do better. You can't do better than this. Yeah? So this is a restriction of computers, of computer arithmetics that you can't deal with. But till this point, you will get the best algorithms that there are right now. And let's switch to the second example. To imagine that for you, multiplying and dividing by 10 is simply moving the decimal point. Yeah, so it's easy. For computer, it's the same with 2. Now, if you divide and multiply by 2, it's pretty fast because from the computer perspective and computer arithmetics, this is binary one. Then this is easy. But there are some roundings, even if you think of the numbers or data that you put in the computer. And this is one of the examples. One of the examples is that if you put 0.1, so 1 over 10, which is, it seems to be pretty number for us, But it has for a computer, it has to be changed into the binary representation. And in binary representation, in binary system, this number has an infinite expansion. But we can't represent something that is infinite. So we have to cut somewhere. And depending on the type of the variable we are using, it will be rounded somewhere. So even if you put 0.1, it's not 0.1 anymore for the computer, even for that. And let me give. So is it painful for us? So first, let us see how we can check it on Julia. We simply use the function bit string of any number you want. For example, 1/10, 1/2. It's this one. 1/10. It will be well, it's infinite but repeatable. Yeah. So you can check it. There is a maybe not sorry. It's not funny. But there is a story that it could be painful. And the story with the roundings related to 1/10. And this story is about the Patriot missile defense. With in Saudi, it got some kind of failure. So we've got the Patriot missile, and the task of this Patriot missile is to intercept an enemy missile. And it was working pretty well. And but someday, enemy targeted the military camp, U.S. camp, and it wouldn't work. Simply, it was launched, and it made the calculations where to intercept it. Unfortunately, it was not succeeded doing that, and some people were killed. You can see. You can see the Defense Technical Information from the Defense Technical Information Center. You can read exactly, because of course investigation were done, and what was the failure. And the failure, in fact, was related to numerical methods. So there were two problems with it. So the first problem was that the time that you need to calculate in what direction should this missile should be launched, then this time was simply a counter of 1/10 seconds. 1/10, 1/10, 1/10, and it was repeating and calculating it. But we already know that 1/10 on the computer is not exact. This representation of this is not exact. And it wouldn't be a problem if this counter was a small one, but it was nothing happened 1 day, second, 1 week, the second week, 1 month, and this counter was clicking and clicking and clicking, and those roundings were generated like in total, aggregated, and it influenced the result. Because if you think about how fast this missile is, and even if this mistake, this error is on the 5th decimal place of the 5th digit of after decimal point, then it's still crucial for this computation. And so there were only not double precision but single precision arithmetic. So after that it was changed. All the system were changed into double precision. And the simple solution was to restart the counter each day, because if you think of 24 hours, it was enough. But if you think of a year or months, the error was and the aggregation of those two errors were too much. And for this one, for this incident, the battery had been operating continuously for over 100 hours. So 100 hours was too much, but 1 day was not. It will be okay. Let me show you. One more example that it's related with arithmetic operations. In here you can see the function, and this function we've got two parameters. So what are the parameters? So let me get this function running. So you can run those parameters with how many times you want to add and subtract the same term. So for example, for this one, you've got 100 of times adding 1 over 2, 1 over 2, 1 over, so a half, 100 times, and then you're subtracting it. With the exact arithmetics, you know what is the result, what should be the result. But if on a computer, if you do this many times, so 100 times, 1,000, 10,000, and you use it for this term, it will be 1 over 2, 1 over 3, or 1 over 10. We can see what will happen. And those are the results. So if you use 1 over 2, which is pretty nice for computer, because of the binary system, then you will get exactly, even if you got 10,000 times or 1,000,000 times, you will get 1. It's pretty easy. But if you get 1 over 3 and you do this 100 times, you've got more or less 1, but it's rather more than less. If you increase the number of times of adding and subtracting the same term, then you will the error will be increasing as well. And of course, it is for 1 over 10 is more or less the same, but in fact, it doesn't have to be more. So it's more in here, it's more in here, more in here, more than 1. It's more than 1 in here, but it could be as well less. So it depends on the term you are using. So you can try it for yourself, getting different numbers, and you can see that what you are thinking about the arithmetics, the simple arithmetics, adding and subtracting, yeah, it's not working on a computer properly. All right, so let's switch to another example. We want to use Julia to calculate some values, but you can use as well Google calculator for that. And obviously those, so you've got the sinus of 0, pi, and pi multiplied by any integer, you should get 0. You don't have to use computer for that. You know what is the result. But what will happen if I've got like incredibly big number multiplied by pi, and billions or more? So let's see how what will happen in Julia. So I will start with, there is an approximation of pi. It's not exact value. It's a constant, but of course you can't represent it exactly on a computer. Well, you can calculate it with accuracy, whatever accuracy you need, but it still won't be exact. So even if you want to calculate thousands or 10,000 of digits, then you can do that using Julia, but it still will be an approximation at some point. So almost any number is an approximation on the computer. So let's see what will happen. So this is, if I'm using a float 64, then so this is the approximation of pi using this type, and it's valid. Of course, if I use sinus of 0, I will get 0. If I use sinus of 2 pi, then I will get something that is close to 0. Close. If you think about this arithmetics, and I told you that this double precision is 16 places after decimal point, so this is more or less that. But after that, if you are increasing by 20 to 2,000 or 2 million or any even bigger number, then the accuracy will be lowering. Like this accuracy, it's less and less, and after that, instead of 0, you get at almost 1. So imagine that this is not the target, but you are using this number in other calculations. So if you are using this in other calculations, then you will get I'm pretty sure that the results that you will get will be completely stupid. So what was happening here? It's not about sinus function. So the sinus function, calculation of the sinus is working properly. But remember that this is only an approximation. So if you multiply it by millions, then you will move this digit farther and farther. And after that, you will there were some cutoff points. So in fact, it's not sinus of 2 million of pi. It's sinus of something close to 2 million of pi. How close? No, unfortunately, not so close anymore. So it's not about sinus. It's about multiplying by some kind of approximation of pi. And this is the problem. So not with calculating it. Probably everyone should. It's a quick exercise how to deal with it if you want to get a better number. Yeah. So you simply instead of calculating so many pi's, you should get to the range from 0 to 2 pi, and then you should calculate it. And then it will be well with better. It will be much better. Julia, it's pretty like MATLAB. MATLAB is also for numerical analysis. It's pretty great. It's expensive, but good. So Julia is free of charge. Yeah, you can use it. And it's also got some implementation for specific function. If you want to get it exact solution, I mean exact, you can use special functions for that. So if you are for this accuracy acceptable for you, it's okay. But for some problems, we even know how to calculate with exact accuracy. So you've got special functions, and I will give you 2 examples only. So the first example is if you want to calculate, if you want to compute e to the power of x, so any x minus 1. So you can use this one, and this is only an approximation, but also there is another function. It's xm1, it's called. And if you calculate it, there is a special algorithm behind it that gives you an exact solution for that. And the same with the natural logarithm. So if you want to get a natural logarithm of 1 plus x, then you can use logarithm of something. But if you want better accuracy, then you should use log 1p. And you can see that there are some discrepancies between them. This is so they are close. It's not completely different, but they are not exact. So till this number, they are exact. After that, they are wrong, and the same in here. At the end, you can see there are some differences. So if you want to get a better accuracy, look for specific algorithm of calculating only this. Only this. Unfortunately, in most of the cases, you have to deal with some kind of approximations, but in special cases, and those special cases are used in specific tasks. Like if you want to get some kind with normal distribution, and you got the e to the power of something, or with the logarithms, if you want to get the Taylor series for that, then you should use better functions, and in Julia they're already implemented. I've got a few more examples, so I will speed up. Let's get the 4th example, and there are 3 numbers, and I want to simply add it. And if I use the paper, an order of summing them, it's not important. I should get exactly the same result. The question is, what will happen on a computer? And this is not software specific. It's like in any case, you will deal with this kind of problem. So those are the 3 numbers. You can see what is the result by adding them yourself. And I will switch to Julia to give you different. I used only 2 of those, but you can try all of the possibilities. So those are the cases. So the first one I use 50 plus 100 minus 150. And in a second, I start with 100, then I put minus, and then exactly plus. So the real answer, the exact answer is -1. So using this one, I will get exact solution. So this is a. If I change the order, I've got something that it's close, but not exactly the same. And this is due to the precision of the arithmetics. There are some roundings, and you can't fight it. You can change the arithmetic precision for that if you need. But there still be an error, but not at the 8th place, but at the 16th place or more. Yeah. So you have to think how good accuracy you need. Yeah? For that. So even if you it seems so, imagine like that. Adding for computer is complicated. Multiplication, and if you want to multiplicate on the computer, it's not a problem. It's not a problem for the computer. It takes longer than simple addition, but it got not numerical errors for that. Adding numbers or subtracting numbers, it's problematic for computer. If they are close to each other, you can get any error you want. Yeah? If they are closer and closer to each other, there should be 0, but in fact, it's not 0, but 1,000,000. And you can fight it. Yeah? Well, you should fight it, but you should be aware of this one. So it's not a problem with the software. It's not a problem with the computer. It's a problem because of the roundings and the specifics of the arithmetics. And those are simple. So using special tasks like machine learning, artificial intelligence, predictions, you've got plenty of those operations. So we can think, okay, so how accurate this solution is if inside it made so many errors. Yeah. Let's get another example. I will use, I use both an Excel and Julia for inversing a matrix. And this matrix is given on a slide. And of course, so the first task is to calculate an inverse of this matrix, and the second task is to verify if this is really an inversion. And how you can verify it? I will simply calculate a times a to the power of -1, and I should get an identity matrix as the result. And let's see for this specific matrix. If you use Excel, you can try it yourself. Simple. I put print screen for that. Not to waste time on doing that. So I've got the matrix, then I've got the formula of calculating an inverse matrix. So I've got something. Yeah, it's hard to say if it's okay or not. But after that, I want to check it, and this is the result. So it's not an identity matrix. It should be, but it's not. So the question is, probably error is because Excel is not great. It's not meant to be used for mathematics, but still it's a little bit surprising. Yeah? So let's see how Julia is dealing with this problem. In fact, you can calculate simply inversion of the matrix, but I know that there will be an error, so I put it with try and catch, yeah, to look it better. And if you do that, it will give you the singular exception. Why? Because this matrix is non-invertible. So I said that Excel is not good. Yeah, it's perfect because this software like Julia or MATLAB is not. We can't calculate inverse of a matrix for the non-invertible metric, but Excel can. So maybe Excel is better. But in fact, using this for numerical methods, it's much wiser because you will get an error. Not in every case, but in some cases you will get an error. From Excel, you will get a result that is completely stupid. Yeah. And by the way, the explanation what happened during the Excel calculations was that it was supposed to be dividing by 0, and dividing by 0, okay, it's singular, I can do that. But in fact, it wasn't 0, it was close to 0, like 10 to the power of minus 16, 10 to the power of minus 15. But if you want to divide by this number, it's pretty easy, because instead of 10 to the power of minus 16, you will get 10 to the power of plus 16. And this is why you've got in here so big numbers, because it should be 0, but it's not during these computations. So Julia, MATLAB, or Octave, like the free clone of MATLAB, those are the softwares you should use this kind of computations to get reliable results. I mean, or to give at least a hint. Okay, you shouldn't do that. Maybe it's not possible. Yeah, to calculate it. So this is singular. You can calculate determinant, or you can check it yourself. That you shouldn't get any answer for that because it doesn't exist, simply. All right. So this was 5th example. Let's get to the 6th one. And the 6th example is solving system of linear equations. But in fact, I don't want you to show how to solve it. It's not the case. I will do something easier. I will give you the solution. So this is the system of linear equations. So you've got the right side, you've got the matrix, and you've got an approximation. I tell you the truth, this is only an approximation of the solution. Approximation because I used only 4 digits in any case. So this is an approximation. And the task is how to check how good this approximation is, or is it okay to say it is as a solution? Is it a solution? Is this particular x is the solution of this system of linear equation? So probably the easiest thing is to substitute into the equation and see what is the difference. So to find the residuum of the system of linear equations. So I will find the residuum of the system of linear equations, and based on that, I will ask, okay, do you believe this is the solution or not? So let's try it. So if you do that, so this is the matrix. This is the right side vector. This is the solution that is given, and I will show x, a, I will show b, and after that, so we've got it, and I want to check what is the result if I get b minus a multiplied by this given x, by this potential solution. Right now it's a potential solution, and you will get, of course, for the ideal solution, you will get 0, 0, vector of 2 zeros. But we are using computers, so probably you won't get any, like it's almost impossible to get 0, exactly 0. But in here, you've got something like a number multiplied by 10 to the power of minus 8 in both cases. So we've got, and the question is, should we believe that this is a solution or not? And in most cases, during the most of the students usually say, okay, yeah, it's pretty good, like 8 decimal places, it will be better than, even if I use a paper, probably I will make a mistake, so it's much better than that. All right, so let's check the solution. It's a stupid algorithm. You shouldn't do that. You shouldn't calculate an inverse matrix, but let's solve it using an inverse matrix, because we know the formula for solving it, and use Julia for that. So I will calculate inverse of the matrix and multiply by b, and this will be my new x, not given but calculated, and I will check what is the result. I mean, what is the difference? So in here I've got 10 to the power of minus 8, and in here I've got 10 to the power of minus 9, 10 to the power of minus 10. So it's better. Slightly, like better accuracy. It seems better. All right, but with system of linear equations, you really shouldn't do that. I mean, you really shouldn't use a computer to calculate inverse matrix unless you want to check the result of your on a paper. But the task is not to calculate an inverse on a matrix. The task is to calculate the system, to solve system of a solution, the system of linear equations, to get the solution for that. And to get the solution, you don't need to calculate inverse. because in Julia there is a special arithmetic operator you should use to solve system of linear equations. And I will use this one because it's the proper way to do from the numerical perspective. So don't do that. Use this one. And if you use this one and you will check, then you will get the result. Not 10 to the power of minus 8, not 10 to the power of minus 10. No, you will get 10 to the power of minus 16 minus 17. So in fact, it is like exact solution for a computer. So if you use smart algorithm, you will get the solution. So let's compare the solutions. Because I also know the exact solution. So exact solution is 2n minus 2. So if we use this, you can see it's not exactly the same, but the magnitude of error is the same. More or less 0, yeah, for that. So if you want to compare it, you'll get like, for the given it was almost 1 and minus half, and the exact solution is 2 and minus 2. So it was not even close. So so if I show you this without showing the rest, probably most of you said, oh yeah, this is the solution. Yeah? It's not great, but it's close. But if I show you this and say how close this one is to this one, probably not so close. Yeah, you wouldn't say it's a solution. Yeah. So even checking if this is if this is a right solution could be challenging. And solving is completely different thing. So you should use proper algorithms and proper software to deal with mathematical problems. All right. This was easy. I mean, easy, only 2 variables, but those 2 variables means that it's not a problem with a number of variables, because you will need time to solve it. But you still can get better solution with millions of variables than with the system of linear equations with only 10, but hard to solve for a computer. Let's get another example. This is a Hilbert matrix. So Hilbert's matrix, the formula is pretty easy. I put it in here, but just to get a clarification for that, if you use not the diagonals but this opposite diagonals, you will get 1 over 2, 1 over 3, 1 over 4, but not on the diagonals, but in another direction. Yeah? And I want to solve system of linear equations with this matrix, this type of matrix, for different size of the matrix, like 5 by 5, 20 by 20, or 100. And I want to, so I can use any right side vector. In fact, from the numerical point of view, the problem with solving system of linear equations is only with the matrix. So the right side vector is not important, in fact. So you can use any, and you will get, of course, if you've got only zeros, you will simplify your computations, but the matrix could be difficult or challenging for a computer from the numerical perspective point of view, but not the right side. So I will use this right side vector. I can get only ones, but you can get anything you want. And I will verify, of course, the results, calculating the residuum of the system of linear equations. You can use it as well if you are curious. You can use it also in Excel and check how Excel is okay for that. But for this one, I will use this is own implementation of Hilbert's matrix. You can use any you want. It's one-liner, so in fact you don't have to use function for that. But I implemented Hilbert function. And for that, so I've got the function, and I've got another function that is used to solve system of linear equations with the right side vector that consists of the ones. This one remark. The second remark, I use this previously implemented Hilbert matrix to build a matrix, in fact, and I used a stupid algorithm with inverting a matrix. I told you not to do that, so I want to be sure that you remember that. And I will show the, so for this one, I will show the norm of the residuum. Because for 2 by 2, it was easy to track, like the vector of two numbers. With 5 by 5 will be easy. But if I want to run it for 100, I don't want to see 100 numbers. Yeah? So I will calculate the norm, and you can calculate the norm, the second norm, or the inferior norm, like the supremum norm for that. Okay, you can use any norm you want. And I use it for n equals 5, on n equals 20, and n equals 40. You can continue it if you want. It's pretty easy. And in here you've got the results. So I will comment those results. So in fact, those are only five numbers from the solutions, like first five from the vector of solution. So it's the full solution in this case, but in this case, there are only 5 out of 20 and 5 out of 40. And you've got, in ideal solution, you will get the norm equals 0. But this is not ideal world. We are dealing with computers. So for 5 by 5 matrix, Hilbert matrix, you will get the result and the norm of the residuum 10 to the power of 12, minus 12. So not 0, but probably acceptable. But if you increase this size of the matrix with 20 by 20, then it's not a mistake. It's not like 60 and it should be multiplied by e to the power of, no, it's 60. And in here you've got 100. What does it mean? It means that, first of all, the Hilbert matrix is an example of a matrix that it's really bad for the computing. It's really hard to deal with it. You have to use the proper algorithms. You should always use the proper algorithms, but if the matrix is nice, then even if you use the bad ones, then you will probably get a pretty good solution, like actually with good accuracy. But if you are not lucky and you should handle the matrix like a Hilbert matrix, and it's only 40 by 40 or 20 by 20. Yeah. So imagine what will happen if you use 1,000. Yeah. So you have to use a specific algorithm for that. If you don't, probably you can get randomly numbers and you will get better solution than that. Yeah, use random numbers for that. And if you want to see the part of this solution, all the inverting. So what is the problem? The problem is not because this matrix, we can't deal with it. We can, but the problem is that we are dealing with the system of linear equation, solving of system linear equation by calculating inverting the matrix. You shouldn't do that, and you don't have to do that because there are plenty of other ways of solving system of linear equations. So you should use those other methods, not this one. And the problem with this one is with calculating the inverse matrix is like that you can calculate the inverse, but the accuracy of it is not great. So for 5 by 5 is acceptable. For 10 by 10, maybe it can be acceptable, but for 20 by 20 and 100 by 100, the rounding errors and arithmetic errors are so great that they are influencing the result of the system of linear solution of the system of linear equations. But you can, in Julia, do better. So if you are interested in getting the exact result, you simply can switch the type of the matrix. So those were the real numbers, the floats. 64, but still. But you can use the rational number for that. And if you calculate inverse of the rational number, so this one, it should be an identity matrix. So there are ones on a diagonal, but not zeros of diagonal. Close, but not zeros. But if you use rational numbers for that, you will get exact solution. So this is the Hilbert matrix. So you'll get 1, 1 over 2, 1 over 3, 1 over 4, like this. And if you calculate inverse matrix and you want to verify it, you get exactly identity matrix. It's slower, much slower, yeah. But if you want to get an exact result, you will get it in Julia. There are not many softwares that can do that, in fact. But there is a special type for that, not to lose the accuracy of the numbers. Yeah. So you can use it to solve system of linear equations better. And how to use this better? Even if you don't want to use those rational numbers, you can use the better algorithm for that. Yeah. 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 Okay, with million, I wouldn't try to. I'm not sure how long does it take, but if you've got time and memory, like million by million is a lot. Yeah. Okay. So creating, I don't believe that you've got enough memory to to keep this matrix, and you want to construct it. But for example, if you want to calculate and you get your own type and own algorithm using rational numbers, and you are interested only in one row, one column on a one number, not needed to calculate all of that, then yes, you will get an exact result with rational numbers. Yeah. For example, with system of linear equations, there are some formulas if you want to get only one element of the vector, not the full one. You don't have to, you are interested only in the first one. Or in physics, you are not interested in all of the vector elements of the vector. You are interested only in this energy that is like minimal energy. Yeah, so you want to get an eigenvalues for those, but not all of them, just the greatest or the smallest in this case. So it depends how you treat this one. So if you want to find only one, then you can do better. And in this one, I can. Okay, I will. I can use not 5 by 5, but let's 10 by 10. Yeah. So it's you've got still 1 by 1, but it takes time. Yeah. You saw that I can get 100. I can't get this one. Okay, so this is too big. Yeah. This is because one. Okay, 100 by 100. So you have to deal with your own type for that. So you have to implement something. So the 100 big one. Yeah, is big one. It's growing pretty fast. I mean, yeah. So this is due to the overflows. Yeah, it's simply yeah. You have to calculate binomial for the, it's big. Yeah. So you have to change the accuracy and using big ints for that. Yeah, but it's possible. Yeah. I mean, this is like factorial. If you want to calculate factorial of 100 and you deal with this like normal types, it will be too much. But if you've got big ints for that, not because I used for that, this is rational and only 64 in 64. So you have to use something more for that. Yeah, but it's possible in Julia. Yeah, it's possible in Julia. I'm not sure how long does it take if you've got thousands or 100. Yeah, but in here, so probably 30 or 40, it's acceptable for that. It should be. Oh, almost. Okay, almost overflowed, still overflowed. Huh? Yeah, but this is for this type. So if you use rational numbers, not with int 64 but big int, it will calculate. Yeah, it will calculate with any accuracy you want. I simply you have to implement your own functions for dealing with big int. Yeah. Some of them are, I believe, most of them are already written. Yeah, so you can do that. And if you've got the solution using better algorithm, so special operator to solve system of linear equation in Julia, and it is the same as in MATLAB. Exactly, it's working like this. It will choose automatically a method depending on the metrics. So if it's a sparse matrix, you will get different algorithm of solving something. If it's small matrix, you will get different one. If there's special like structure of the matrix, you will use different one. So it's not one algorithm, one method. There's a set of methods automatically detecting which one we should use, and you can see that it's still not ideal solution for that, yeah, but pretty. It should be once, yeah. Everyone should be once, because we know that the right size vector was 1, 1, 1, and so it should be like that. One, so it's not one, but 1 point something, yeah. And you can of course change type of this one to get a better accuracy as well. In Julia, you can do that. All right. Oh no, one more example from here, and how to define from numerical point of view that the matrix is bad or not easy to deal with. You should calculate the condition number. So the condition number defines if it's the best condition number. If you use the norm, the second norm is 1, and it doesn't. So it's not the same as the size. It's not the same as the determinant. No, it's got nothing to do with it. But the condition number, if it's 100, you can live with it. 1,000, probably yes. But with the Hilbert matrix, the condition number is in millions. So this is why it's a problem. Yeah? So you have to use the special arithmetics for that if you want to solve not exact, but with high accuracy. And in here we can see a condition number of the 3 diagonal matrix. So if I put on a diagonal 2s and above and below -1s, and this is the matrix that you should know from many fields, like from the Laplacian discretization or plenty of others. So it looks nice, but it's not strictly diagonally dominant. So it's exact, yeah? Like you've got 2 on the diagonal, -1, -1, so it's like exact. But you've got plenty of zeros. And of course, the best approach would be, if you want to solve system of linear equations with it, you can use linear methods, like in linear time, your own implementation, and you can use millions of variables to deal with it, because with 3 diagonal matrix is easy. Like diagonal time of solving it's linear dependent on the size of the matrix. With lower or upper triagonal, it's n squared. So if the size of the matrix is n, then you need n squared computations to solve system of linear equation with lower or upper triangular. With the full matrix, you need n cube computations. So it means that if you increase the size of the matrix by 2, like twice bigger matrix, you will spend 8 times more for computations to get the result. So with bigger matrices, you have to wait. I mean, you still have to wait. But with this 3 diagonal matrix, you can see that you can get a matrix, and you can get a condition number. It's simply a function cont of A, and you can plot it, and you can see that it's increasing. So it means that if you want millions, you will get the same problem with the Hilbert matrix. So you have to use the special algorithms for that. So it looks nice, and it's nice if it's small. If it's big, it's not nice anymore. And of course, for many years we already know how to deal with this kind of matrices. Yeah, I only want to show you the condition number that is increasing, and you can check the same thing for the Hilbert matrix, and you can see how bad is there. It's pretty bad. I mean, in millions, billions. Yeah, it's increasing pretty fast. So if you've got a matrix and the condition number is small, and even if you choose bad algorithm, probably you will get the result that with high accuracy that you can call it solution. If the condition number is big, then you have to get special arithmetics or special algorithms for that. Or you can use Julia algorithms, because somebody already implemented it. You don't have to implement it on your own. Okay, so this is for the Hilbert matrix. So for this one, it was 150. For the matrix size 20 by 20, for Hilbert matrix is 10 by 10, and the condition number is 10 to the power of 13. Okay, so this is an example of really, really bad matrix for if you want to check. All right, so we've got one more example, and this one more example is about calculating exponent, like e to the power of any x, and we know how to do that, but I want to base this one on Taylor's algorithm. I mean Taylor's series. So I've got the series, and of course I can't get to the infinity. So it will be exact if instead of n I will get infinity, but I have to end somewhere. Yeah, so I choose n big enough to get a good accuracy, and with this big n I will calculate terms and add them as many times as I want to get some kind of approximation of it, and I will, like it's already written, the Julia program that will verify the results for different x's, like x equal 1, 0, minus 100, plus 20, or something. You've got different x's to check if it's okay, and I want to compare the results. So the comparison will be with the built-in x function, because of course Julia got its own. You don't have to write it on your own. So this will be our own implementation. I will compare it with Julia implementation, the results only. Yeah. And let's move to, and there will be 2 tries. So this is the first draft of the solution. Here we've got 2 parameters. One, because you have to define some stopping criteria. It's iterative algorithm, so I will add, and I've got maximum number of iteration as a 1 parameter. I will put like the default at 1000. You can change it, and this is for x, because of the you have to provide it, yeah, e to the power of what x you want to calculate. And this is an algorithm. So in each iteration, I am calculating the next term. So I'm updating the term, and I will add this to the solution that I already implemented. So first it will be 1, then it will be, so I've got 1, then it's plus x squared divided by 2 plus x to the power of 3 divided by 6, and so on and so on. And in here I want to show some results, and those results okay, this is one function. This is the first draft of the function. Okay, and I want to generate the function. Oh, this is the, maybe this would be better. Yeah. So for this one, or this one, I will put as the result x, maximum number of iteration it was used, what is the result from Julia, what is my result, and what is the difference between those results. And I assume that it won't be exactly the same as in Julia, because it's not a good implementation of this for this problem. It's not a good solution for this problem. But I used for different points. And what I'm saying by different points, I put the points from here, like 0, -1. So those are the points. And I use iterations. So how many iterations? For example, for 0, it shouldn't be a problem. Why shouldn't be a problem of 0? Because it should be even two of those maximum iterations. You should get the exact solution. Yeah. With 1, you should more. So I increase it to 10,000. We can check in a moment what is done. So I want to get a lot to get an exact solution. But those are the discrepancies, because of course Julia, the stopping criteria is not the maximum number of iteration only, but the accuracy you want to get. And this is the result. So what is the problem? It's not a problem with 0, because the result is, if you use 10 iterations, you will get 1, and you should get 1. So the difference is 0. If I want to calculate e to the power of n, so e, with 100 of iterations, it's 2.7, so as it should be, and the difference is close to 0. Yeah, so it's pretty good. For 10, there is a difference, and it's increasing, but it is increasing because probably I'm not using enough iterations. So if I use not 1,000 but 10,000 or 1,000,000, I will be closer and closer to this one. Yeah, this is the idea. So it's not so close anymore if you use 50 or 100. But remember, so even if this one, it looks, oh God, this is a big error. Yeah, but the result is also big. Yeah. Because the result is e to the power of 43 in this case, so it's really big number. So the error e to the power of 28 is not so big if you compare it to the result you should get. Yeah, so it looks that it's working pretty well. So let's see what is with negatives. So for -10 you got almost 0. So what should be the result if you tend to minus infinity? So e to the power of x, e to the power of something negative, strongly negative, it should be 0. So it's close to 0, but let's see what is happening after that. So it should be, it's closer and closer and closer to 0 with Julia implementation. What is going on with our implementation? So with our implementation, it was okay with -10. It was not so good, but still acceptable with -25. It was really strange for -50 because it's plus 2,000, and it's enormous number. So instead of decreasing, it's increasing. And of course, you can put more in here to get the result. It will be calculating, but it's not improving. So it is not the case that it's not enough iterations. It's simple and not good algorithm for that. So I will give you the information what is going on. So what is going on is that if you've got for big negative numbers, for big ones, each term is plus minus, but they are pretty close to each other. Yeah, so far away, they are so close to each other, but you have to deal with subtraction of 2 till the absolute value, more or less the same values. And on the computer, it generates error, big error. The closer there are, the bigger error. So if you are pretty close, so instead of 0, you will get millions for that. How to deal with it? Julia works perfectly. Yeah. But we know that it's working for positive numbers. So if you want to do that, so one of the tricks, if you want to improve this solution, so this is why I called it better solution. So if you want this better solution, you should use absolute value of it. So it doesn't matter if it's -10 or +10, if it's -100 or +100. For this computation, you should use exactly absolute value, and you will get it. But at the end, if it was negative, you should get 1 over it. Simply, yeah, because e to the power of -x, x is the same as 1 over e to the power of x. So it's working for positive numbers. So let's use it, and only for negative numbers, let's get some updates of this one. And if you do that, so this is the function, and those are the computations, you will get the results more or less the same as in Julia. So this should be working on the paper, but most of the algorithms from primary or secondary school, you shouldn't use them on the computer. So from a numerical point of view, they are not good. Julia gets the implementation of good algorithms that there are proofs that they are working. So you should, of course, nobody is an expert in everything, but if you want to use something, it's better to use Julia for numerical methods, because at least in some cases you will get some warnings, and you can believe that those results are reliable. Anyway, like the summary, it's pretty like two of those. So one of them, Julia, is providing you the algorithms and libraries that are numerically friendly and acceptable. There are some other softwares as well, but don't use Excel for that. Yeah. And the second, it's like for you, you should be using computer, not computer using you. So you should be smarter than computer, not faster. Computer will be faster than you, but you should be smarter than computer. And to be smarter than the computer means that you should always verify the results, because probably even if you get some mistakes, you will get some kind of number as the result. The question is not to get a number. The question is this number a valid number? And depending on the application, you should be an expert to judge if this result is really a result. In many cases, unfortunately, it's not. So I encourage you to be in the part of the people that are verifying the results and seeing, okay, maybe it's wrong. So I know that computer spends hours and hours of calculating it, but the result, it's not valid in my opinion because, and you will find an error or to find a better solution, better approach, better algorithm for that. All right, so those this is it. If you've got any questions, you can ask now. You can ask me later by email as well. If I know the solution or know the answer for the question, I can give it to you. Of course, those are only the basics. Yeah, so I don't get into details of the numerical methods and theory behind it. Most of the softwares are using the libraries from the 70s. Of the previous century, because there were proofs that they were working. We can do better than that only because we can use, for example, distributed computing. So it's not like more sophisticated algorithms are always better. No, the simple algorithms are prone to parallelization. So you should use also, depending, of course, on your expectation and on the availability of the computer. Yeah? You can use not the CPU, but also the GPU for that. And in Julia, it's easy to do that. All right, so if there are no questions, then thank you for today. So we've got half an hour break. And after that, another interesting topic with optimization problems. And tomorrow, the last day. And I invite you as well for the next day. Thank you.